Log on, tune in, find out. Another good idea from Cambridge.
Final speaker, it's a pleasure to have Simone Linz, who's at the Phylogenetics group in Tübingen, working with Daniel Hussein's group, and she's going to talk on the complexity of the Quartet challenge.
Thank you, Mike. So this is actually joint work with Maria-Louisa Bonnet and Catherine St. John. And to get started with the Quartet challenge, I would just like to recall the notion of compatibility. So for example, here we are given like 3 quartets, which are unrooted binary trees on 4 taxa. And the question is whether there is a single parent tree that explains all the ancestral relationships of these 3 quartets. So well, here is such a tree. And to see that this tree actually embeds all the information you are given by the quartets, you just look for the subtree in that tree here. So you just connect the taxa 1, 2, 3, 1, 2, 4, and 5, and you see that the tree actually is the same than the tree of the first quartet. So then the blue quartet is also a subtree of that tree, and finally the green quartet is also embedded in that tree. So we say that the tree actually displays the quartets. Or in other words, we say the 3 quartets are compatible. So this leads to the following decision problem called quartet compatibility. You're given a set of quartets, and you want to know, is this set compatible? And it has been shown in 1992 by Mike Steele that this problem is actually NP-complete. So a natural follow-up on this question is then, what about uniqueness? So if you're given a set of quartets, are there several trees that are compatible with that set of quartets? And if so, how can we decide? So just to show you and to follow up on the previous example, here is a second tree. So the 2 trees actually look quite similar because they have the same tree shape, but they do not have much else in common. So they are completely different. So it's not clear how to go from this tree to that tree. So then Mike Steele posed the Quartet challenge almost 20 years ago. And he asked, what is the computational complexity of the following question? So you're given a set of quartets. And additionally to that set, you are now also given a tree. And this tree displays the quartets. And then you want to know, is this tree the unique tree that displays Q, the set of your quartets, or is there another tree? So actually, there are several approaches that characterize this quartet challenge. And it has been done in terms of several types of graphs. So for example, Sample and Steele had a characterization on caudal and intersection graphs, and then there's another characterization by Grunewald, Humphreys, and Sample, who showed that the so-called quartet graph and edge colorings via these graphs are related to that question. So still, although there are these characterizations, the computational complexity remained open, and so we tried to tackle this problem. And the first thing we did is we rephrased it a little bit. So instead of asking, is T the unique tree, we are now asking, is there another tree than T? And we call this challenge the Quartet challenge star for the rest of the talk. So actually, if you compare these 2 challenges, then you can see that the Quartet challenge and the Quartet challenge star are complementary to each other. Meaning that if the answer to the Quartet challenge is yes, then the answer is no to the Quartet challenge star. So if T is the unique tree, then there is no other tree. And here's actually the theorem that we proved. So the Quartet challenge star is NP-complete, and by the complementary character of the 2 challenges, this means that the Quartet challenge is co-NP-complete. And in the rest of the talk, I'm going to show you a little bit how we managed to get the proof. So first of all, we had a look at the ASP completeness framework developed by Yato and Sita in 2003. And ASP stands for another solution problem. So basically every decision problem pi prime is associated with another solution problem. And the instance to such a problem is you're given an instance of your decision problem, and you're also given a solution to that instance. And then the question you want to answer is, does there exist a solution other than the one you're given? So this is, in fact, the same flavor than the Quartet challenge star is phrased, because we want to know, is there another tree? So to tackle the computational complexity of these ASP questions, there is the notion of an ASP reduction. And an ASP reduction is a special kind of a polynomial time reduction, which you may all know from proofs that show that decision problems are NP-hard. So to prove that something is NP-hard, you usually use a polynomial time reduction. Now, for an ASP, or what you usually do to prove that something is ASP complete, you start with a problem for which you know that it's already ASP complete, and you take an instance. And this instance is associated with a couple of solutions, so we call it the solution space. Then you take your reduction, and you try to transform this instance into an instance of your problem under investigation, and you have to guarantee that this reduction can be done in polynomial time. So you get an instance of your problem under investigation. This instance is also associated with a space of solution. And then you need to show that there is actually a bijection between the two spaces of solutions. If you can show that there is such a bijection, then you have an ASP reduction. So informally, a problem pi prime is ASP complete if and only if there is another, or if and only if there is an ASP reduction from pi to your problem under consideration. And for pi, you need to know that it's ASP complete. So just like in the case of NP completeness, you always start with a problem for which you already know that it's NP complete, or in this case here, ASP complete. And then Yeto and Sita got this little theorem here, which is actually quite nice. So if a problem is ASP complete, then it's NP complete to decide if, given a solution, another solution exists. So why is that helpful for our problem? So if we can show that the Quartet challenge star is ASP complete, then we know it's NP complete to decide. So it's computationally hard. Okay, so for the rest of the talk, I'm going to talk about several reductions, so ASP reductions, in fact. So we start off with 3-set, and for an instance of 3-set, you have like a conjunction of clauses. Each clause contains 3 literals over a set of variables, and the question is whether there is a truth assignment such there exists a literal that is assigned to true, at least one for each clause. So here we have an example. You have like 2 clauses, each contains 3 literals, and here are 2 satisfying truth assignments. So you can easily see x1 is true, so the first clause, there exists a literal that is true, and x4 is also true. So both truth assignments are actually satisfying under 3-set for this example. So Yeto and Sita showed that this problem actually is ASP complete, and we use this as a starting point for our reductions. So the next problem we looked at is a variation of set. It's called not all equal 3-set with constants. You're again given a conjunction of clauses, each with 3 literals, and additionally you have 2 constants, t and f. And then under not all equal 3-set, you want to find a truth assignment such that t is set to true and f is set to false. And additionally, you have the constraint that each clause has a literal that is assigned to true and a literal that is assigned to false. So continuing with the same example that I showed you before, and the same 2 truth assignments, we can now see that the first truth assignment, which was valid under 3-set, is not valid under the not all equal 3-set, because x1, x2, x3, and x4 are set to true, so no literal in the first clause actually is set to false. And then the second truth assignment is also valid under the not all equal 3-set with constants, because x3, so for the first literal, x3 is set to true, and x1 is set to false because not x1 is also true. And for the second clause, you can also easily verify that it is a valid truth assignment. So then, since we knew that 3 set is ASP complete, we figured out an ASP reduction to reduce the 3 set to the not all equal 3 set with constants. So this problem is also ASP complete. So the next problem we looked at is betweenness, and betweenness was actually used to show that the quartet compatibility problem is hard. So this was the proof by Mike Steele. And betweenness is the following problem. So you're given a collection of ordered triples ABC over a set A, and the question is whether there exists an ordering from A into the first cardinality of A minus 1 integers, such that for each triple you either have that f of A is less than f of B is less than f of C, or vice versa, f of C is less than f of B is less than f of A. Okay, I should go back for a minute. So this problem actually is not ASP complete, because if you're given an ordering, then you can simply reverse that ordering and you get a second valid ordering. So in fact, you can get a second solution in polynomial time, which is bad news. So this problem here, as it's stated, it's for sure not ASP complete. However, if you rephrase it slightly, you can come up with a problem that is ASP complete. And this version is called betweenness with constants. You're again given a set of ordered triples over A, and additionally you have 2 variables m and m, so capital, lowercase and uppercase m. And then you want to figure out or try to calculate a betweenness ordering such that again f of A is less than f of B is less than f of C, or vice versa. And additionally, f of lowercase m is equals to 0, and f of uppercase m is equals to the cardinality of A plus 1. So this means that the lowercase m is always the first element in your ordering, and the uppercase m is always the last. So now you cannot simply reverse that ordering to get a second ordering. And here's an example. So you're given 4 constraints, and actually this one here, so m is less than A is less than B is less than C is less than capital M, satisfies all 4 constraints, because lowercase m is less than A is less than B. Then for the second constraint, you have B is less than C is less than uppercase m. The same holds for the third constraint, and then for the fourth constraint, you again have that lowercase m is less than B is less than uppercase m. So by using again an ASP reduction from the not all equal 3 set with constants, we could show that this problem is also ASP complete. And then the final step in our proof was actually to get an ASP reduction from the betweenness problem with constants to the quartet challenge star. So just to remind you, here's again what is the quartet challenge star. So you're given a set of quartets and a tree, and you want to figure out if there is another tree. And this is the theorem. So the quartet challenge star is ASP complete. This is the theorem we finally get if we do the following proof. So here's a sketch of the proof we did. So as I mentioned, we tried to get an ASP reduction from the betweenness with constants. And so for each betweenness constraint AI, BI, CI, we construct 6 quartets. And this is also the same that actually Mike Steele did for showing that the betweenness, that there is a polynomial time reduction from betweenness to quartet compatibility. So it's not so important to look at the quartets in detail, just to point out a few things. So these 6 quartets can actually displayed by exactly 2 phylogenetic trees. So here are the 2 trees, and each of them is a caterpillar. So you have alpha and beta on either end. Then you have your AI and BI and CI in the middle. And then left and right, you have some additional variables, Q's and some P's. So you have like 2 Q's and 2 P's. And so the P's are always close to the A, and the Q's are always close to the C. So if you now take all the constraints and you add in 6 quartets for each constraint, you get a set of quartets that can be displayed by a caterpillar if and only if there exists a betweenness ordering. However, the problem with that caterpillar is that it's not unique. So if you're given a betweenness ordering, you can come up with several caterpillars that display the set of quartets. So this is in fact bad news for us because we want to get an ASP reduction, so we need this bijection between the 2 solution spaces. So if we are given a betweenness ordering, we want to come up with a single tree. And this is, with that, not possible. So we need something more. And just to give you a little bit of an intuition why the tree is not unique, so if you add in all these quartets, there are no quartets that tell you something about 2 different P's or 2 different Q's. So in fact, the Q's and the P's are not ordered. So we were thinking, okay, we need more quartets. So to follow up on the previous example for the betweenness, so if you add in all the quartets, you can come up with this tree. And as I said, the Q's and the P's are not ordered. So we were thinking, okay, we add in more quartets such that the P's and the Q's are ordered among themselves. And with that, I mean that the higher the indices of the P's and the Q's, the closer they are to alpha and beta. And additionally, we add in some quartets that guarantee that all the P's are closer to alpha than all the Q's. And just to note, it's not trivial because you're given an instance of betweenness, but you're not given the ordering. So you don't know which of the P's are on either side and which of the Q's are on which side. However, if we add in all these additional quartets, we can then prove 2 claims. And the first claim is that 2 phylogenetic trees, T and T prime, that both display the set of quartets, are isomorphic if and only if the 2 trees restricted to alpha and beta and to the part of the middle, which contains actually all the elements in your set A, if these trees are compatible. So this part of the tree here actually gives you the betweenness ordering. And if this part of the tree differs, then you know the betweenness ordering is also a different one. So this is now good news because we know that if the betweenness ordering is a different one, then we also get a different tree. And then finally, we could show that the set Q of quartets is compatible if and only if there is a betweenness ordering such that f of m is equals to 0 and f of uppercase m is equals to a minus 1. And in particular, there is a bijection from the solutions of a betweenness instance to the solutions of to the set of compatible trees that displays Q. And so we have an ASP reduction now. So we know that the quartet challenge star is ASP complete. And by this theorem by Yato and Sita, this in particular implies that the quartet challenge star is MP complete and the quartet challenge is co-MP complete. And that's actually the end. I would like to thank Mike for posing the problem and for some sleepless nights, the Spanish government and the University of Tübingen for funding, and the Isaac Newton staff and the organizers for this workshop. Thank you very much.
Thanks, Simona. There's time for 2 questions. Steve.
ASP framework can be weakened or generalized a bit. So not just saying, is there another solution, but are there K more solutions? Is there anything known
So
about
it's
it?
always hard if you're given like K solution. It's always hard to get to the K plus 1 solution. This is also in the paper by Yato and Sita.
Any other questions? Well, it just remains for me to present the award. I'm glad I actually bought one of these, so I was pleased that your talk didn't have the 0 case.
Thank you very much.